Hey guys, it's Mrs. McBride here. I'm sorry I'm missing your class today. I have a meeting that I need to go to. Hopefully you are wonderful and good students for Mrs. Borzik while she's here. Okay, so a couple of notes before we move on. I wanted to talk to you today about static friction. So in the lab that you did, you looked at kinetic friction, which is basically moving friction. Okay, static friction by definition is stationary friction. Stationary, I can't spell, stationary friction, okay? Or the friction that you must overcome for movement. Friction you must overcome for movement, okay? So like if you wiggle your butt around your chair, you don't move, right? You don't fly off your chair because there's some amount of friction that's keeping you there. And the nice thing is that the equation here, FF equals mu Fn, is the same. There's just, we put this little teeny s in there for static. Okay, that this is static friction. Okay, any questions about that? Okay, flip the page here. Wonderful. Okay, now it says, draw a force diagram representing the force of static friction on a level surface. Okay, so if here's our object, okay, and I'm telling you that some force is being applied, we know that friction is acting opposite of that force. Okay, it's acting opposite the direction of motion. Just like air resistance, friction is always slowing us down. And just to be, good here, let's add in our other two forces, okay? And if any time I go too fast, this is a video, so you could sit here and stop it as you want, okay? Now, this next box here is asking us to draw friction while we're on a ramp, okay? So that ramp is at some angle. Here's a box that's on that ramp, okay? So what forces are acting on it? Well, you might say that, well, of course, gravity is pulling this down, okay? And the normal force is acting perpendicular to the surface. And then the box is going to move this way, but there's no actual force pulling it. But since the box is going to move this way down the ramp, we can say that friction is acting in this direction. I hope that makes sense. Okay? Now you, unlike me, have some stuff filled in here, and I told you to leave some space there. I'm sorry, there's a legit fight outside. I just got a little sidetracked. It looks like somebody is handling that though. Okay? How does the magnitude of kinetic friction compare to the magnitude of static friction? Okay, well, we're going to say that the static friction is going to be larger than the kinetic friction, or the force of static friction is going to be larger than the force of kinetic friction. The reason why this is it's based on the materials, but we know in general that it's harder to get things started than to keep them moving. Right? Think about you're trying to move something really heavy, right? You're trying to push a heavy couch or a filing cabinet, right? And it seems like it takes a little while to get it moving, but once you get it moving, it's a little bit easier to keep it moving, right? That's because the coefficient of static friction to overcome movement is larger than the coefficient of kinetic friction, or the force of static friction is larger than the force of kinetic friction. I hope that makes sense, okay? If I come over here, we're not going to do this example problem, but we are going to do this example problem. This one says a 10-kilogram box rests on a ramp that is laying flat, so basically on a flat surface. The coefficient of static friction is 0.5. The coefficient of kinetic friction is 0.3. Okay, so again, static is larger than kinetic. What's the maximum horizontal force that can be applied to the box before it begins to slide? Okay, so if it's before it begins to slide, that tells me that it's not yet moving. So what type of friction are we dealing with? I hope you said out loud static, right? Static friction, okay? So the maximum amount of force would be equal to the force of static friction, right? Okay, these two forces would be equal, okay? Once this one is larger, then these actually begin to move, right? So the point at which these two are equal is right exactly when this begins to move, okay? So I know that FF is equal to mu Fn, right? So I can plug that in there for FF is equal to mu Fn. Now the next part is kind of tough. Well, what does Fn equal? If we look back in our notes, we know that there's no equation for Fn. Okay, so what we need to do is we need to say, well, Fn must be equal to some other force. Okay, if we're on a flat horizontal surface, the normal force is equal to what other force? I hope you said it's equal to the force of gravity, right? That the normal force is equal and opposite to the force of gravity. And we know that the force of gravity equals mg, so we can substitute in here that Fn equals mg, or we can write out that F equals mu mg. And this is good whenever we're on a flat horizontal surface, okay? So we can say that we're going to use the static mu, which is 0.5, times my mass, which is 10, times little g, which we can also use as 10. So if we do this math, we get 0.5 times 10 times 10, or we should get 50, right? And over here, it said what force is necessary to keep the box sliding at a constant velocity. So this tells me that it's moving, and if it's moving, then I'm going to need to use the coefficient of kinetic friction, or in this case, we're going to cut right to the chase here, and we're going to say that the force is going to equal mu mg, or this is going to be the coefficient of kinetic friction, 0.3, times the mass, 10, times little g, 10, okay? And this should give us that the force required to keep it moving is 30 newtons, or as we could see, is less than it was required to get it started, okay? I'm gonna make another video. I'll see you in a second.